Yeah, good morning, everyone. So today we will begin the session with a talk on graph theory titled Exploring a Graph through Sage. The speaker is Dr. Nitin Singh. He's a PhD from mathematics and he's also worked in the industry for 5 years. So now I will hand over the stage to Nitin.
Okay, so thank you all for coming on Saturday morning. And I see some people have to leave straight to airport, so I'll not try waste their time. Okay, so the talk is about graph theory and via this software called Sage, with which you can actually experiment with graph theory. So just before I start, I would just like to know how many of you actually have had a formal course in graph theory. That's roughly 50%, I guess, right? And how many of you have heard of graphs in like an algorithms course or something? You must have seen graph algorithms, shortest path, Dijkstra's, all that. Okay. So today, the focus is not so much algorithmic. We'll study graph theory for graph theory's sake, but since every other computer algorithm is on graphs, so that will probably help you even designing better algorithms. And yeah, so what's going to be here is a bird's eye view of graph theory. So what are the different kind of questions we ask about graphs? What are the different situations that we can model using graphs? And as I said, the second part is to actually introduce you to this software called Sage, with which you can do graph theory and a lot of other mathematics like linear algebra, calculus, or polynomial solving. Basically anything. All right, so let's get started. So we'll start with the almost the first problem on graph theory. Can I make it? Okay, I can't make it bigger, right? Okay, that's about it. So it's the text is getting squeezed into the corner. I hope you can see that. So this is probably the first problem in graph theory. So there's a city called Königsberg, a mathematician called Euler happened to be there, and there are 4 islands A, B, C, and D, and they are connected by bridges. And Euler asked, let's say, can you start? So you have a hotel over here, maybe A. Can you start at A, take all the bridges exactly once, and return to the starting point? So taking all the bridges exactly once. So that's what we wanted to know. And so he expressed this as a graph. So you can put a point down for each island, and you can put an edge for each bridge. So in graph theoretic terms, this translates that can you start at a point, take each edge exactly once, and return to the starting point? Or one of those newspaper puzzles where you trace this figure out without lifting your pencil and without going over any edge more than once. So Euler unfortunately discovered that you cannot do this in this particular graph. And why, does anyone know from before? Why is it not possible so what you have to do is start at some point of your choice, take every edge exactly once, and return to the starting point. But Euler discovered you cannot do this in this particular graph. And the reason is so let's start at A. A is our hub. Suppose let's say from A I go to D, and now I have to go out of D, so I'll take maybe one of these edges. So suppose I take this edge. So I take from A I go to D and then take B. And now you see I already have a problem. Why? At some point I need to cover this edge, right? I have taken this edge and this edge, but at some point I need to cover this edge. But to cover this edge, I need to somehow come to D again. Is that right? I need to come to D again, maybe via C. But I've already used these two, I cannot repeat. So the only way I can enter D again is via this edge, right? But then I cannot leave D, because I have used this, and this. So I cannot return back to A. So in this graph, and you can repeat the argument starting at any vertex. So if you try to start from B and go anywhere, you'll discover, let's say we started at B, and you took your first edge to A. So you reached A here. Okay, you can get out of A, no problem. You can maybe go to C. But now you see you have exhausted 2 edges of A. And there are still 3 edges remaining at A. So you definitely have to enter A once again, somehow. So maybe you enter through this edge. You enter A. These 2 edges are remaining still. Now you maybe leave by this one. You see that this edge is still remaining. So you still need to enter A at least once. Right? This edge is remaining. So maybe you enter like this, but then you can't leave. So you remember you started at B. So again there is a problem. So can you guess what is actually causing the problem? Why are you getting stuck? You feel free to give a wrong answer also. And yeah? Okay, so what's the problem with degree of nodes? Yeah. So you'll see that if any node has odd degree, you cannot actually complete this tour. Why? Because forget the starting point. Consider the point. So suppose you have to start and end at this point. For every other point, every time you enter, you have to leave also, right? So every time you visit that point, you consume 2 edges of that point. So that means if you enter, let's say k times, you will end up using 2 k edges. So every node apart from the starting point at least should have even degree. Because you enter, leave, so it's in pairs. But then starting point you used 1 edge initially. For every visit in between you use 2 edges, entered, left, and in the end you will use 1 edge again. So when starting point needs to have even degree. So what we have is that if at all such a tour is possible, all vertices in your graph should have even degree. That's the minimum requirement. So Königsberg unfortunately is not a well designed city, so you cannot do this in Königsberg. And just some random jargon that you're seeing there. This is the way to construct a graph in Königsberg graph in Sage. This is very easy. You just call. So here our graph has multiple edges. Normally when I'll talk about graph in this talk, apart from Königsberg graph, a graph will not have multiple edges between 2 vertices. So between 2 vertices we'll always have a single edge at most. But since this problem, I can't go back in time and change how Königsberg looked. So we'll stick with multigraph for this problem. So yeah. So that is the way to create a graph in Sage. So all you say is put these vertices, put these edges, and then you can just show the graph and shows it like this. Okay, so now we know that if at all a tour is possible, you need every vertex degree to be even. So let's just modify this graph a bit and make every degree even. So you get this graph. So what we have done is every degree was odd. To 2 vertices you added this, and to other 2 vertices you added that. So now every degree becomes even. So can I find the tour now? Can I start at one point and cover all the edges and return to the starting point? Yes? You sure? Okay. So it is yes. So in fact you can check using Sage again. So in Sage the command is Eulerian. So if a graph admits such a tour, it's called, because the problem was started by Euler, so a graph is called Eulerian if you can have such a tour where you start and take all the edges and then to the and you can in fact see what that tour would look like. So the Sage gives you. So it says this is so you can ask for the Eulerian circuit of the graph, and it says if you start from A, you go to D, D is your next one. Using edge, because it's a multigraph, I have labeled the edges, otherwise the edge is defined by the 2 vertices, but here because between 2 vertices there are more edges, so I have labeled. So you take the edge called E from A to D, then you take from D to E, and you can see the solution. You can complete the tour and return to A. Okay, so now the question is, how do we show that if all vertex degrees are even, you can do it? And that's Euler. I don't think Euler showed it, but if he tried, he would have showed it. So this is the theorem of Euler. A connected graph has an Eulerian circuit if and only if all vertex degrees, all vertices have even degree. And we'll just hint at the proof, because and part of the charm of graph theory is in it has very elegant and very clever proofs, and that really is, yeah. So I'll at least try and give one or two proofs today. Not too much, but one or two. So let's see. Like to use a bit of board. Say marker pen, yeah. So now you have a graph. So this, where we know every vertex degree is even, and we want to find. So we basically want to find a circuit that covers all edges, something like this, and does not repeat any edge. So okay, so we attack it in steps. So every vertex degree is even. So can I say that if every vertex degree in a graph is even, then it will at least have a cycle? As in you can, so I'm intuitively assuming you know what a cycle is. You go from vertex to vertex, and so if every vertex in a graph has even degree, it will have a cycle. Why? Yeah. That's a good answer. So she's saying you start with any vertex, you go to a vertex, because degree is even, you still have a free edge. So you take that edge, you enter a new vertex. You again have a free edge because you have consumed only one edge. At some point you'll have to repeat a vertex, right? So you started from here, you go to new edge. So at every vertex I enter, I still have somewhere to go where I have not visited. So because number of vertices is finite, some place I have to repeat a vertex, and you get a cycle. So okay, so every vertex degree is even. So what do? I have some cycle over there. I take the cycle out of the graph. So delete these edges from the graph. So every vertex which is in the cycle lost two edges, right? And every vertex which was not in the cycle, it did not lose any edge. So again your graph again has all degrees even, right? So if you started with a graph with all degrees even, and you took this cycle away, the remaining graph, again all vertex degrees are even, because you either lost degree 2 or you didn't lose anything, depending whether you were in this cycle or not. So I can take another cycle out, right? So I take another cycle out, let's say this, and again the remaining graph has all degrees even. So I can keep taking cycles out of this graph, right? Okay. So let's say at some point no more edges are going to be left, right? So you keep doing this, at some point you will exhaust all the edges in the graph. So once you take the cycle out, you delete those edges. So now the only thing is, should be able to, so let's say we got these cycles out. Now just remember that the initial graph was connected, right? So all these cycles cannot appear like this disjoint. So that means this cycle touches somewhere one of these three cycles. So maybe, so this cycle is maybe attached something like this. Now you consider these two together. They should touch somewhere because the whole graph is connected. So you cannot get a partition like this. So it should be linked somewhere to this cycle. So this way you can combine the cycles and you can get. So when you join the cycles, you have that property that you can start from a point and end to the. So that means this graph will actually have a circuit, and it actually sort of gives you an algorithm to find one. What you do is take a cycle out, keep taking cycles out, and in the end, just stitch those cycles together. So yeah, so this is one example where an obvious necessary condition that all vertices should be of even degree actually turns out to be sufficient. And you would want to do this in some cases. So suppose you are an airline and you have a brand new aircraft and you want to fly these routes. You would want to do it in a manner where you don't have to repeat a route. So you probably invest your time finding the Euler's circuit in that graph. Okay, so that's about. And let's see one more example of Euler circuit. So it's a well-known graph, octahedral. So in Sage, all well-known graphs you can just give their names. So it's an octahedral graph. So here also all vertex degrees are even, and you can ask Sage for the Euler cycle, and it gives you like you start from 0, or 0 has gone above the. Okay, so that's bad. You can either see the answer or you can see the solution or see the graph. Yeah, but you can find. Yeah, can find on your own. So the next thing I'd like to cover is something called a matching. This is the main focus of this talk. So if you have to take away one thing, just remember there's something called a matching in a graph, and it's particularly useful in the context of bipartite graphs. So first I'll just say what a matching is in a graph. So since everyone here knows what a graph is, it's just a collection of vertices and edges. So matching in a graph is basically any collection of edges which don't intersect. So no two of them intersect. It's like, so from a big graph, a lot of edges, you just take some collection of edges which are pairwise disjoint. That's a matching in a graph. So if your graph is bipartite, the matching would pictorially look something like this. I mean, they can physically cross, as in your drawing they can cross, but the endpoints have to be distinct. And very often you are interested in finding a matching of maximum size. Just to get you familiar a bit with the matching, let's say I have this graph star. What's the matching of maximum size I can get in this graph? 1, right? Once you pick an edge, you cannot pick another edge because all edges are intersecting this edge. Okay. So let's see some situation where you may require a maximum matching. Okay, so a matching is called perfect. A matching is called perfect if every vertex gets a matching edge, or every vertex is matched. If you can match every vertex in the graph, you call it a perfect matching. Okay, so let's say this is a cabinet problem. So on the left side are ministers and on the right side are ministries, and the PM has asked these ministers to indicate their interest for a ministry by drawing an edge. So if this minister is interested in ministries, he just draws an edge to that ministry. And what has to be done is to every minister, you have to assign a ministry to every minister which he or she is interested in. So this essentially translates to finding a matching in this graph. So you assign one edge, and those edges should not intersect. Unfortunately, the size of every figure is just that you can see 90% of it, I think. So okay, this is the whole graph. So this is some, they have their preferences. So do you have, so what's first is using Sage you can find if, so perfect matching in this case would be that you can find a matching of ministries to ministers for every minister. So there are exactly 5 ministers and 5 ministries. Yeah. Full screen, is this, it's already full screen I think, okay, that's slightly better, yeah, thanks. So let's just see if there is a maximum matching, and this you can find using Sage. So first you have to build a graph, and the graph building is over here. Okay, I've said hide, so I'll unhide it. So it's easy to build a bipartite graph in Sage. You say it's a bipartite graph, and the vertices on the left side, you give a list of vertices which you want to be on the left side, you give a list of vertices which you want to be on the right side, and then you just connect the edges. Now this I had to do manually, and then you can plot this graph, which Sage will show you like this. So once you have built the graph, you can ask for a matching in the graph, and so you can ask matching in the graph, and it gives you this. But you don't have to read it. You can actually ask it to draw matching edges in different colors. So the matching edges are drawn in blue. So there may be many different matchings possible. I'm not saying this is the only one, but in this graph you could find at least one. So PM is happy. Yeah. third part, oh none, okay, don't bother with that. So edges, normally that should denote the label of the edge, but here we don't bother labeling the edges, so there's none. Yeah, that's the way it displays. Yeah, so third parameter is normally for the label of the edge, that's not there. Okay, so that is the practical part, how you can do using Sage, but let's just discuss why would you not find a matching, or why would you find a matching in a graph. So we'll consider the bipartite case because it's simpler, and that is, this is the main. So you have a bipartite graph. So everyone knows what a bipartite graph is. So bipartite graph is one where you can partition the vertex set into two sets such that each edge goes across the partition. So let's say you have some graph. I must point out that sometimes you may not be given this bipartition explicitly. It's easy to say it's a bipartite graph if somebody gives you it like this, but sometimes, okay, for example, is this a bipartite graph, this tree? Is this a bipartite graph? Everyone says yes? Yes? Okay, why? Okay, so you're saying you can create a partition by taking vertices at odd levels and even levels. So, and every edge goes across the partition. Yeah, so it's a bipartite graph. Right. Okay, so let's come back to the problem of finding a perfect matching. So perfect matching in a bipartite graph would be when everything has a matching edge like this. So what can be the obvious problem? Why can you not get a perfect matching? Some obvious obstruction to perfect matching. And this, I think I have it somewhere. Okay, we've gone too far back. Yeah, for example, if two ministers, they want a single ministry, both of them, their interests are very narrow. So you have, let's say, these two. They are not interested in anything else. They are both interested only in this thing. Then you can't find a perfect matching, right? Because this one you assign either to him or to him. You cannot. So because he has no other interests, once, let's say, you pick this edge, there's nowhere to go. There's nothing to give to this person. So if two ministers or two vertices over here just touch one vertex over here, you cannot find a perfect matching. Somebody has to be left unmatched. More generally, what you can say is, sorry, shouldn't have rubbed that. But let's say, if you have some k people here and they together touch less than k over here, then you cannot find a perfect matching because somebody has to be left out then. Okay, but suppose I told you that this graph has the nice property that any set of size k, and if you consider its neighborhood on the right side, it's at least size k. So every set of size k here touches at least k people here. Then can I find a perfect matching? And Hall's theorem says, then you indeed can find a perfect matching. So this is again, the theme is very similar to the last problem. There you had a condition that, I just have to simply, the theme is that there you had an obvious necessary condition that every vertex degree has to be even, but when that condition was met, you actually could solve the problem. Here also you have an obvious obstruction that everything on the left, everything of size k on the left has to touch at least size k on the right, but if this obvious obstruction is not there, you can actually solve the problem. Okay, so I was planning to do only one proof, and I'd like to give you a proof of Hall's theorem. So that if such a condition is true, then you can actually find a perfect matching. Okay, so this is the trickiest part, in some sense the most, because I said graph theory is about elegant proofs, so at least you should see one of them. So let's see, how do we go about it? So we'll proceed by contradiction. So I am given a graph. Just remember the property of this graph. I'll denote by this, or let's say n. By n, I'll denote the neighborhood of set S on the left. Its neighborhood on the right, I'll denote by n of S. And all we know is n of S is always bigger than cardinality of S. So I want to find a perfect matching here. So what do? I say my graph satisfies this condition, and I ask somebody to give me a matching of maximum size that he or she can find. And suppose that person gave me this matching. So I'll say if this is the best you could find, then this has to be a perfect matching, right? And so at least I can perfect matching. You can also sometimes we say that you match this side completely. So if there are more people on this side, you cannot obviously match everyone here. So we'll say you match this side completely. So why? So he says this is the maximum matching he can find. So let's see. I say this has to be perfect matching, otherwise something is wrong. So what I'll try to do is, if this is not a perfect matching, so there is somebody unmatched on this side. So let's say I start with this person. He's unmatched. He doesn't have a matching edge. And I'll ask this person to find somebody on that side that, so there are some edges going out. Let's say edges denote that he knows that person on the other side. So I'll say, can he find somebody, can he know somebody who's also unmatched on this side? No, right? But because then I could have added this edge, so then this is not the maximum matching. If there is somebody on that side which he knows and he's unmatched, I could have just simply added this edge, and then I'll say this is not the maximum matching. So this matching M is the maximum matching in this graph. So that means what if he does not know anybody? So I'll try some other people who are unmatched. If no one knows anybody on this side, then also this is the maximum matching, right? And this is the best you can get. Oh, no, sorry. So what we are given is this. We are given this matching, and we are given this that this condition holds in a graph. We have to show that this matching is, so the best matching has to be perfect matching. So if somebody here is, if you have some person here who's unmatched, he has to know somebody on this side. Why? Because of this condition. See, this is one person here, so its neighborhood has to be at least 1, right? So he has to know somebody over there. If this somebody is, if this somebody happens to be unmatched, then I will say I have a contradiction. This was not the maximum matching in a graph. So let's say this somebody is somebody who is already matched. Let's say I go here. So now we start a game, sort of. This person throws he has a volleyball. He throws it to the person he knows. People on this side have a very simple rule. If they are matched, they just throw it back to their partner, right? So you throw a ball here, this guy throws a ball here, so now the ball is back in this team. Now together there are 2 people, right? So together they must know at least 2 people on the right side, so they can throw a ball to somebody who have not. So here is only one person, so somebody else is there who one of them can throw a ball to, right? Let's say this person knows somebody else. Let's say that person also happened to be matched on this side, right? Now the rule is very simple for people on this side. So on this side, this player is covered, this player is covered. He throws the ball back to his partner, so you get here. Now you see there are 2 people on this side, and you get 3 on this side. So there's, again, you can throw the ball. One of them can throw a ball to somebody, right? Let's see. How can this game possibly end? So as a good graph theorist, now you start this stupid game. You forget about what happens in between, and you just ask, how can this game possibly end? When will it end? When one is, you cannot pass the ball to a new person, right? But will that situation arise on this side? No, right? Because on this side you have always one more the number of players on this side is always one more than on that side, and by this condition, you should have somebody who you can throw the ball to. Now the thing is, how can the game end on this side? If you throw the ball to somebody who's matched, he will just throw it back to his matching edge. That means only way the game can end on this side is if the ball is thrown to somebody who's not matched. So that means, suppose it comes something like this, right? So it start. Now what you do, once you reach this person who's unmatched, you reverse the ball throwing. So you retrace this path back to that person. So what you do, I should have drawn edges in different color. So let's trace this. When you throw a ball from this side to this side, you mark it in green color. So let's say this, he threw to this person and he came via this black matching edge to this. He threw again in green color to this person, and he via matching edge he came back to this, and finally this could throw a ball to here, which was unmatched. Now you consider this retraced path. So you retrace from this. So you have a green edge, then you have a black edge, then you again have a green edge, okay, so, and yeah, you have a green edge. You reach here straight away, right? Maybe you could have more. In this particular example, there isn't, but you could have more sequence of. So what it starts with an unmatched person, ends with an unmatched, because he started the ball. Ultimately, you have to trace back to him, right? He started the game. Now what you can do, just for variety, I'll just make this path a bit longer for illustration. So suppose you had one more round of zigzag. So you had a green edge and a black edge, and then finally you reached. Now you be clever, you say I'll remove these black edges from the matching and put these green edges in the matching. So you have increased the size of the matching. You've replaced these two edges. That means the original matching was not a maximum matching. You found a bigger matching. It's a contradiction. So that means you should have had a perfect matching in the first place, because otherwise you can enlarge it. So that proves that if this condition is met, the matching of maximum size has to be a perfect matching. It should match everybody. Yeah. Otherwise, you can enlarge it. So it sort of also gives you an algorithm how to improve a matching. So the way you improve a matching is by finding such an alternating path from an unmatched person to an matched person, and then replace the matching edges by those alternating edges. So this can be implemented in polynomial time. So you have a polynomial time algorithm for finding a maximum matching in a bipartite graph. It's not true in a general graph. But in bipartite graphs, it's very efficient to find a maximum matching. So this problem, for example, can actually be solved quite easily. And Sage does it for you in polynomial time. So, okay. So in this ministry, you can indeed find a maximum matching. Let's see some other situation where you might require a matching. So you may not have a perfect matching, but you are still interested in the biggest matching you can find. So suppose you are looking to form the biggest doubles, as many doubles team in tennis you could form. So this is a problem people have at Wimbledon. So what they do is they get 7 top men's players on one side, and they get 6 female players on other side, and they want to pair them up. They want to form doubles teams. Now if everyone liked playing with everyone, the situation would have been simple. You pair anyone with anyone, but that doesn't seem to be the case. So the edges denote that these two people are willing to play with each other. So now this graph is a randomly generated graph. So Sage can generate a random bipartite graph for you. In particular, it does not contain any of my favoritisms or bias. So it just happens. No one wants to play with David. It's a random graph. No one wants to play with David. So what is the best size? So in a very good situation, you would expect, because there are 6 on this side, 7 on that side, you expect you can form 6 doubles teams. If everyone liked everyone, you could have formed 6 doubles teams. But let's see what is the size in this particular graph. So you can ask Sage for a maximum matching in the graph, and Sage finds this. So you see, in fact, 2 people are left unmatched. Absolutely no bias. It's just a random graph. So it turns out the maximum matching you can get is of size 5. I mean, Rafa was ready to play with Petra, but somebody else took her. So Yeah, and he had very limited choice. Maybe if he had more choice, he would have found somebody. But let's run this again, because this is a random graph. I want to show you how Sage can generate. So we can run this again. So this is basically an HTML page. You write the program in your browser. You press the evaluate button. It gives you. So there's some nonsense. Key line is R equal to graphs random bipartite, 7 on one side, 6 on one side. 0.3 is probability of putting an edge between any two. So it generates a random graph. Remaining nonsense is just to make the vertices look like this and not 0, 1, 2, 3, 4. So basically we are generating a random bipartite graph and basically copying it onto this graph. Whichever edge is in this graph, we copy it to this graph. Let's run this again to get a different graph. So you get some different graph. Now it's okay. Oh, this is really bad. Very few edges. 3 of them have absolutely no interest. You cannot hope to get a really good matching in this graph. Okay, we can try again. So let's try and get the matching. Okay, that is plotting the graph. Yeah, let's try and get the matching in this graph. Obviously, I mean, these 3 people did not show any interest, so they obviously will not be matched, but the remaining, it seems, we got a matching of size 4. Yeah. Let's run this once again to get something better than this. This is really a group that does not like each other very much, this particular. Let's try once more. Okay. No one wants to play with Andy this time. And we can try once more what the matching we get. So again, maybe the best you could have hoped for was 6, but you can get 1, 2, 3. Oh, you can get 6. The best. So all the female players are matched, at least in this side. All the ladies players are matched. Yeah. So yeah, it's a random. So randomly you can get. So the size of So the size of the matching is the number of doubles teams you can form. So let's, so in both these situations, the cabinet and the doubles team, the bipartite graph was sort of given to you. It was clear from the situation. But there can be situation when you have to be a bit clever to identify what the bipartite graph is and what the edges are and whether you are looking for a matching at all. Now, this next problem that it doesn't look it has anything to do with any matching. So it's Latin squares. So Latin square of order n is what? It's basically an n cross n array where every row and every column contains a different number, and the numbers are from 0 to n minus 1. So like this is a 4 by 4 Latin square. This keeps appearing in the newspaper, so you probably know about it. Another problem is somebody gives you a partially filled Latin square like this. He fills, so it's a 5 cross 5, he fills 2 or 3 rows, and then he says, can you complete it? So he partially fills, and when he is partially filled, he has filled it correctly up to that point, as in nothing is repeated in a row or column up to the point he has filled. The thing is, can you complete this to a full Latin square? So what can this, so can we complete it? So the trick is, can we complete it row by row? So I am given something which is valid till this point, can I put the next row? So what possibly can it have to do with any bipartite graph or matching? What do you have to match to what, and why should you a perfect? So you probably want to look for some perfect matching, matching of what and what. Yeah. Okay, rows on the left side. You say okay. So we have a graph. Okay. So one, okay, rows on the on one side, yeah. So but what will be on the right side, and what do you have to?
You can have the row column position on the left side.
Okay.
Possible number, like the numbers 1, 2, 3 on the other side. Possible.
Okay, so she's saying you put. So you're basically saying this cell, these cells on the left side. You put these cells. So you put these cells on the left side. You can denote by the row, comma, column number. Or since you are only worried one row at a time, you can just denote it by the column number. We know which row it is. So let's say I'll just put column on the left side, C1, C2, let's say till Cn. So consider you have n sorry, can I get a better mark? Yeah. Yeah. Okay. Right. So let's say we had n cross n array. This is n cross n, and let's say r of them were already filled for you. R of them are filled in a nice manner. And we are trying to fill this r plus 1th row. This is the one we are trying to fill. So this is the ones we are trying to fill. So, okay, I'm just saying, he also said that you have to take these cells on the left side, so I'll just denote them by the column numbers C1, C2 till Cn. They're on the left side. What's on the right side? So let's say 0 to n minus 1. These numbers are on the right side. And what will be the edges in this graph?
The possible options.
Yeah, so C1 will be joined to those numbers which have not already appeared. So those are the possible numbers that can appear over here. So you connect C1 to those numbers which have yet not appeared. So in that column, so you get some graph. But now how do I say this graph will have a perfect matching? So you get some graph, right? So let's say these were the cells. For each of these cells you connected it to those numbers which are not there already. So remember Hall's, so we have to verify that, so we have to use Hall's theorem here. What we have to show is, if you take let's say any any set of size k, let's say size k on this side, it should touch at least k numbers on the right side. And how do we verify that it touches k numbers on the right side? So okay, first question, how many, suppose r rows are filled out of n, so how many edges go out of this vertex, a particular vertex on the left? N minus r, right? So all vertices on the left, n minus r edges go out of what is. So if I have a set of size k, how many edges will it send out? K into n minus r. Now all these edges have to be consumed by this set on the right side, right? Now ask how many edges come to a vertex on the right side. Okay, this is so a particular number gets hit from how many columns? So okay, it's slightly tricky. So let's say, or it's another way of asking, let's say the number 1, in how many columns does it not appear? Because if it does not appear in some column, that column will send an edge to that number. In how many columns it does not appear? 3. But in that general setting, what it will be? Yeah. Yeah, so the number of times it has appeared is because it appears only once in each row. So if I have r rows filled, a particular number has appeared r times, once in each row. But you can count column wise also. So it has appeared in some n minus r columns, right? If it has appeared n minus r times when you count row wise, it has to count n minus r counting column wise also, right? So again, this also gets n minus r edges only. On the right also you have n minus r edges. So everything gets, so this set of size k sends out k into n minus r edges, and each vertex can consume n minus r edges. So you need at least k vertices on this side also, right, to consume all the edges. So that means this has to be greater than equal to this, which is greater than equal. So Hall's condition is satisfied in this graph. That means you can find a perfect matching. So once you can find a perfect matching, you just put the number according to the numbers according to the perfect matching, and then you can go row by row. So you fill this row, then you can fill the next row. So again you'll have to find a perfect matching. So again sort of gives you an algorithm how to complete a partial Latin square. So every time you build a graph, find the perfect matching in the graph and put the numbers. Yeah. that's it. So I think beyond this point there's not much thinking required. So now it's just you have to watch. Any questions so far till this point? Right, so what are some of the other things we study about graphs is, one is famous vertex cover. So suppose you have a graph which, let's say, models roads in a city, in probably like some in IAC. In the IAC the arrangement is not as pretty as this, I can tell you. But let's suppose this is the road network of IAC, and what do? You station a guard maybe to watch for dogs on that road. And I am personally very scared of dogs, so I prefer if a guard is watching that particular junction. And that's all we demand of our security. We don't ask for much, but keep us secure against dogs. So now the question is, how many guards do you need so that all roads can be watched? And this precisely, so if you translate into a graph theoretic setting, it's saying you want to choose the minimum number of vertices which touch every edge in the graph. So for example, in this, the red, if you take the red vertices in your set, you end up touching every edge in that graph, and you actually cannot remove any of them. Like you will see some edge will go untouched. So if I remove 7, the edge 7, 9 is not covered by anything, and that is called the vertex cover in a graph. In general, it is algorithmically very hard to compute. There is no polynomial time algorithm known to compute a vertex cover in a graph. But in bipartite graphs you can, but I'll not give the proof, but the hint is maximum matching. You can compute the maximum matching and pick suitable vertices from left side or right side. You have to cleverly pick, so you'll get a vertex cover. But we won't do that. We won't do that proof today. But let's just see how using Sage you can compute. It's very easy. You just build a graph. Let's say we take the octahedral graph again, and then just say, give me the vertex cover. And this is just to say that plot the vertices which are in the vertex cover in red color. So you get this. So this is a vertex cover is in fact quite big here. There are 6 vertices and 4 of them happen to be in vertex cover. So somehow this graph is, you need a lot to cover all the edges. What's a vertex cover of this graph, for example, is very small. Okay, give me an example of a graph where vertex cover is just one vertex. Star. Yeah. So the trick, the difficult problem is to find vertex cover of minimum size. You can always, if you include all vertices, that is a vertex cover. It's not the minimum size. Okay, so closely related to vertex cover is the idea of dominating set. Here you are not trying to cover every edge, but you are trying to make sure you cover. So there is a graph. This set D is called a dominating set if for all vertices which are not in this set, there is a direct edge from D to the, as in they touch somebody inside D. Then this is called a dominating set. Where might you need a dominating set? To give you a very graphic, violent example, if you had to secure all these points, you're in charge of security. So you can put, where should you put your snipers so that every location is secured? So assuming that sniper can shoot along a straight edge. So either a sniper should be there in that place, or that location should be directly adjacent to one of the snipers. But let's leave that violent situation aside. You can find this situation in a chessboard. So you know how a knight moves on a chessboard, right? It moves like this way. And now somebody asks you, how many knights do you need to totally dominate a chessboard? As in every area, every square is attacked by some knight. So how many rooks do you need, for example, to attack every area on the every cell on the? A rook is this elephant, moves horizontally. And how many rooks do you need? 7, 8. Yeah, I think you need 8. Yeah, because 7 may not do, because diagonally it cannot. So if you put on 7 rows, something on the last remaining row will be unattacked. rooks diagonally. No, whichever way you will, and if you put 7 rooks on a chessboard, one row will be left, right? One row will be left totally without a rook, right? There's no way you can, so some square on that row will be, yeah. How many queens? Okay, that's difficult. Queens, I think you can do just with 5. Well, I don't have the solution here. You can do it using sage after you go back. But yeah, 8 rooks will totally dominate a chessboard. So let's see how do we translate this into a graph theory or dominating set problem. So what should be the graph for this? So this is just modeling. How do you this is more about modeling a problem as a graph theory. So what should be the graph in this case? So you're trying to see how many rooks do you need to attack every squares. So what's the obvious graph here? So an obvious graph here is actually the squares on the chessboard. They are the graph, as in like you have 64 vertices, and you draw an edge between 2 vertices or 2 squares if your knight can travel from. So for example, a knight can travel from this to this. So your graph looks. It's a really pretty graph, you can see. So this is the graph. So you have 64 vertices in your graph, and you draw an edge if a rook can move from that position to that position. And now can you see that asking how many rooks dominate the chessboard is same as saying what is the size of dominating set. So which means that either you should have rook at that place, or some rook can attack that place, right? That's meant by dominating a chessboard. So what you're really worried is size of the dominating set in this graph. Oh, by the way, is this graph bipartite graph? Is it? What is the bipartition? There's a very natural bipartition here. The chessboard itself gives you. Sorry? Yeah, the black squares on one side and white squares on the other side, because rook always changes the color. When you make a rook move from black square, you end up in a white square, and when you make a move from white square, so all the edges go from black squares to white squares. Yeah, knight. Oh, sorry, not rook, knight. Yeah, knight. It's a knight's move. So now we can just ask Sage to compute. So we build this graph, and that's the way you build that graph in Sage. It's really very simple. The first part is just to place the vertices at nice position, so that you place the vertex x comma y at x comma y, so that the graph looks nice. Otherwise, Sage might have drawn something completely, intangible. And once you have built the graph, you can ask for its dominating set, and you can in fact see the dominating set. Here it's a very symmetrical dominating set. I have no idea why this symmetry is coming, because maybe chessboard is symmetrical. So you place the rooks on these blue squares, and you can see that whole chessboard is attacked now, and 12 is the minimum you can do. That's what Sage finds out. So in general, dominating set can be much smaller than a vertex cover. Note that vertex cover is also a dominating set. Vertex cover, you cover every edge. So if there are no isolated vertices, you still end up hitting every, so it still dominates, but in general a dominating set might be much smaller than a vertex cover. And in fact, in this particular graph, dominating set is just 12. If you computed the vertex cover, so vertex, it's a bipartite graph as people told here. So one obvious vertex cover for a bipartite graph is you take one of the partitions. You might get a smaller, but in this case, for example, squares of one color form a vertex cover. So vertex cover is actually 32, and because it's a bipartite graph, the size of matching is also 32. I told you a theorem that the size of the matching in bipartite graph is same as vertex cover. Okay, so let's come to the last thing. This is about drawing graphs. So planarity. That is, if you can, so far we have not been concerned how to draw a graph. For us, it's just you draw it some way that captures the relationship. But sometimes you want to actually lay down a graph so that the edges don't intersect, and this is you have these three houses A, B and C, and this is like gas, electricity and water. All these three houses need pipes. You can curve the pipes. You're free to curve the pipes or take them anywhere basically on the surface of the earth. But what you want is that these pipes, no two pipes should meet in the middle, because you probably don't want gas and electricity coming together, something. So can you draw it? So you want to, it turns out that in a plane or on the surface of the earth you cannot draw, however hard you try. You will have to cross somewhere. So this is same as saying you want to draw this bipartite graph. So bipartite graph here is this three houses on this side, and gas, water, electricity on this side. So one way to, this is the easy way of drawing, but then everything is intersecting in the middle. You don't want this, so you want to draw in some way that doesn't intersect. But actually you cannot do it for this graph. For graphs where you can do this, that's called a planar graph. And so it's important for circuit design engineers. So they want to lay down a circuit and they don't want wires to intersect. So if the graph is planar, you well and good. If not, they generally try and decompose it into planar graphs. Right, so that's so for example, you can see any tree would be a planar graph. Tree you can always draw. This is K4. So complete graph on 4 vertices. Is this planar? Is this planar? Yeah, you can draw it. So it's not drawn in a planar way in this drawing, but you could have just taken this edge from outside. So it doesn't say that every drawing of the graph has to be planar. You can find one way of drawing which is planar. And if you ask Sage to draw it in a planar way for you, to draw this. This is the same graph as the above. All 4 vertices are linked to each other. K5, this is not a planar graph. The 5 vertices connected to each other. No, I'll not prove it in this class, but take it. This is not planar. In fact, the other Kth, this bipartite graph and this graph, they are used for characterizing planar graphs. So one of them has to be present in some form for a graph to be non-planar. Some form, I'll not say which form. But if one of these is present in some form, then the graph is non-planar. Otherwise, graph is planar. So this is also non-planar. Then you have this. Then you have this cube. Normally we draw the cube like this. But you see, this is a non-planar way of drawing a cube, because edges are intersecting. But you can actually draw a cube in a planar way. How you just push this small square, big square, and it's a planar way. But Sage has a more artistic way of drawing a cube in a planar way, which is like this. I don't know, it doesn't have the geometric intuition. And this is a planar drawing of octahedron. So this is what you normally, this 2 pyramids. Okay, I'll struggle. This thing. So this is a non-planar drawing, but Sage can put it down in a planar way for you. In fact, boundary of any such closed thing is a planar graph. That's also one of the, it's again a difficult theorem. So much for planarity, but just there was one more picture, and I just want to point out that if the surface of the earth was not spherical but something more exotic like a torus, you could actually have drawn the pipes without them intersecting each other. So you can, because you could have taken the pipe down and brought it from up. You can see this figure. You can lay down houses and water, gas, and the pipes can come. And so this graph, while you cannot put it on a plane, this bipartite graph on 3 vertices on each side, you cannot put it on a plane or a sphere in non-intersecting way, but on a torus you could have put it. So something planar might be actually you can draw it on a torus. So okay, so that brings us to the last thing, and then we are done. And there's again not much to be said. So this is just a different. This is just to cover different things that graphs are used to model. And the last thing is graphs can be used to model flow networks. And now Sage has a serious bug. It cannot put vertex edge labels like sort of separate from the edge, so you cannot see. So but just imagine this is an electricity distribution network, and this is your source and this is your sink, and what these quantities denote is the amount of electricity you can send over this edge. So this is like 9 units. You can assume it's a Delhi electricity network. It has been in the news a lot recently. So 9 units you can send, 4 units you can send across this edge, 2 units you can send across this edge, and 3, and this is, I think this is 8, should be 8. This is 3, this is 10, this is 5. And so essentially we want to find how much flow we can send from here. This is the source, this is sink. The only condition it should satisfy is that none of these intermediate nodes, they don't store anything. So whatever enters here should leave. So if like 6 units enters here, then it should leave via 6 units should also leave via those. So again, you can use Sage to compute the flow, and it can draw the flow graph for you. So it says you send 5 units here and 4. So you can send a total of 9 units in this particular network. You send 5 units here, you see that 2 units goes this way, 3 units goes that way, and then this 3 unit carries. So this edge is not drawn because there is no flow along that edge. So Sage gives you the graph only when. So you can see that you can send 9 units of electricity from this point to this point. So this finding a flow in the graph is also, that's also a major graph theoretic area where you want to find a maximum flow possible in a graph. Again, it will take that's a complete separate topic on itself. I just wanted to introduce that graphs can be used to model flow networks. All right, that, yeah. So, yeah. 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 So what you give is not the value, but you give the capacity. Maximum you can send on that. Yeah, and then it can give you the maximum possible flow, the maximum possible you can send. So because you might have a very high capacity on this particular edge, but somewhere down the road you have something of very low capacity. So the high capacity here doesn't matter. You cannot send that. In fact, there's one of the very really good theorems. Probably if you take graph theory in your graduate, you will learn max flow min cut problem. So you can actually, the maximum flow you can get in a graph is the cut is something like this. If I disconnect this vertex, so this, if you see the capacity here, just to give you a bit of heads up, you can send 9 units here, 4 units here, right? So you cannot hope to send more than 13 because 13 is the maximum that can leave from here, and nothing here generates any additional flow. But you could have cut this graph somewhere like here also. So if the capacity is like 8 plus 2 plus 4, so that's 14. So 14 is also, you cannot go more than 14. So any such cut you make, you will get some capacity across that cut. And because you are generating flow only at source, across any such cut your flow, so whatever flow you can possible is not going to be greater than that capacity. And it turns out the cut of minimum capacity is actually the maximum flow that you can get. So this is also in that same league that you have an obvious necessary condition that any cut that you make in a graph is an upper bound for your flow, and you can actually get that much flow. So that's a max flow min cut theorem, but that takes normally 5 lectures to cover in a CS course. I won't try it here. Right, so that's so you saw 5 or 6 examples of where you could use graphs, and that's the end. And installing Sage, if you wish to go back, and it's really easy. You go to the website. They give you a huge binary. It's a 500, 600 MB download. Then you simply compile it. It has everything that it needs. It still has Python, everything. So on Linux, you can simply unzip the tar file and just do a make install. That it will do it. And then it gives you a web interface like this. It also has a command line interface, which I cannot show you unfortunately here. So you can either do in a terminal or you can do in a web browser. All right. Thanks for missing your breakfast and coming here. And if you have any questions, be free to answer.
Do you have any more questions?
Everybody is hungry probably.
So
Okay.
we will thank the speaker and we will give him a
Thank you.
CSA T-shirt.
Yeah. Well, that's what I came for anyway. I mean, I hope you got something out of it. I got this.